Okay, it looks like it's time to start. Does anybody have any questions, and can you hear me for that matter?
We can hear you.
Awesome. All right, I just want to finish off what we were doing about staging last time. So if you look at this phase diagram for lithium cobalt oxide, it's a calculated phase diagram, but it's pretty close actually to the truth, especially with respect to this H13 phase here. This is a stage 2 phase where each of the occupied layers is about 24% filled, and then there's half the layers are emptied. You know, so you sort of wonder, why is the stage 2 not in the middle like it is for graphite? Stage 2 is at the 50% filling. Layers are completely full, completely empty. Bear in mind, in graphite there is a stage 2L phase also. But it's interesting to wonder, why is the stage 2 phase over here way at low lithium composition? So this is the question, you know, why does staging occur at low compositions in the layered hosts and not at x equal to half for stage 2? And this should keep you awake at night. And remember, staging occurs due to the attractive in-plane interaction caused by lattice expansion. Is this lattice expansion more prevalent somehow at low intercalate compositions for layered hosts like lithium cobalt oxide and titanium sulfide and tantalum sulfide? Well, here's a graph that shows you the layer spacing, the spacing between titanium planes in lithium TiS2 as a function of the lithium content. And you can see that there's a strong lattice expansion. You know, the layers get farther apart. Expansion is about 10%. And most of this expansion happens over the very first part as you add lithium up to about 40%. So because the lattice expansion is happening initially as the layers fill with lithium, you know, this is where the attractive interaction is the strongest and where you'll find the staging effects. Once you get out here, there's really no advantage to putting lithium close to one another because the layers are already fully expanded. So just the conclusions of this part of our treatment of staging. You know, staging is important. It affects the way that lithium intercalates in layered systems. It affects voltage composition curves. So I've shown you there's little features that appear in the voltage composition curves for lithium cobalt oxide and lithium TiS2 and so forth. And on homework number 4, I'll give you a couple more questions about staging too. Okay, so any questions about staging before we move on to the next part of the course? All right, I hear no questions. Okay, so I'm going to change to a different PowerPoint, which for some reason is not showing up. There it is. Okay, can you see this new PowerPoint? It's the one I emailed you this morning.
Yes.
Yep.
Okay, good, thanks. So, you know, we talked about very simple models for calculating voltage curves of lithium battery electrode materials. We used a very simple picture of the lattice gas model, where basically we say the host is nothing more than a provider of sites for the lithium. And the lithium occupies those sites, and when it fills them, it has a binding energy, And as lithium, fills more and more of the sites, there's interactions between them, either repulsive due to the Coulomb and screen Coulomb interaction, or attractive because of the strain-mediated attractive interaction. So it's a very simple baby, if you like, model for what's going on. And of course, with modern computation, one can calculate voltage versus composition curves for lithium battery materials. And the details of this are beyond the scope of our class, but it is worth spending one lecture on it just to show you and give you a sort of a flavor for how it's done, and to give you some examples through homework of how useful or not useful it can be. So I want to describe how this is done, okay? And I think the best thing to do is to just go to the document camera for a second. So I'll do that. So I told you earlier that the voltage of a battery is minus delta G over.
Hey, Jeff.
Yeah.
Oh, never mind. Your screen wasn't full here, but now it is.
Is it okay?
Yep, looks good now.
Okay, I don't know what was going on. It's probably just a delay. The voltage of an intercalation battery is negative delta G over NE, where delta G is the free energy change of the full reaction that's taking place in the cell. So we did an example earlier in the class where we said 2 lithium plus half an oxygen went to Li2O. And we calculated the voltage of a lithium oxygen battery that was undergoing this particular reaction. So if you know the free energy of the reactants, you can calculate delta G. The problem is that in many cases, these things have never been measured for the materials that are of interest to us. So what we need to do instead is try to calculate something very similar to the free energy of formation of these different materials. And what we do instead is we calculate something called the total energy of a compound. And what is this? Okay, that's what I want to talk about first. What is the total energy? Well, you assume that you have all the nuclei and all the electrons of the material at infinity. So that means you take the nuclei and you put them far, far away from each other and from all the electrons. You take the electrons and you put them far, far away from each other and all the nuclei. So they don't interact at all. Okay? So the nuclei and all the electrons at infinity. And that's 0. Okay? And then when you bring the nuclei and the electrons together, and they form the appropriate crystal structure, and the electrons occupy the appropriate core level wave functions and valence band wave functions, the total energy is reduced because, there's Coulomb interactions between the positive nuclei and the negative electrons that lower the energy. So the point is, if you are using quantum mechanics and Coulomb's law, you should be able to calculate the total energy of a material. Your goal is to minimize the energy with respect to the positions and wave functions, the positions of the nuclei and the wave functions of all the electrons. So that's the goal, right? And how that's actually done is beyond the scope of this class. Okay, so now we're going to go back to the PowerPoint. What is going on here? Okay, I don't know. Can you see my PowerPoint now?
Yep.
Yes, I can see it.
Yep.
Okay, that's good. It sometimes takes me a long time to go back to the PowerPoint for some unknown reason. Okay, so I've used my document camera to give you some idea of what we mean by the total energy. And typically what happens is you already know the crystal structure that you're going to be talking about. So it's not like you throw a bunch of nuclei and electrons into a bag and say, okay, come out and find me the minimum, the structure that minimizes the total energy. Things aren't that sophisticated yet. Instead, you say, look, I know the crystal structure. Maybe it's the lithium cobalt oxide O3 structure, but you're not sure what the lattice constants are. So you're not sure about the interatomic distances and that kind of thing. So you give a computer program the basic lattice constants. You tell the computer program what the atoms are, which determines the properties of, how many electrons they have. And you let the thing go. And you minimize the total energy by relaxing the lattice constants. So letting the lattice constants move, changing interatomic distances until you find the minimum total energy. And then you say, okay, that's the structure that should result. And often you compare those lattice constants to experiment. Because if you made some errors in the way that you're doing the total energy calculations based on the approximations you're making, you'll get incorrect lattice constants. So at least you have a check on what you're doing many times. And these type of programs are similar to Gaussian. Gaussian is used for calculating properties of molecules. And for solids, where you have, instead of just 100 atoms in a big molecule, you'll have 10 to the power 23 atoms in a solid. But fortunately, solids are made up of repeating units, the unit cell that is just repeated over and over. So for lithium cobalt oxide, the O3 unit cell, everyone has represented it in homework 1. You know what it is, and that just repeats throughout all space. So solids programs like so-called Abinit and VASP do things like Gaussian, except on the unit cell of a solid. And they expect that unit cell is just to repeat like bricks in the wall of a house throughout all space. Okay, so really the key for us is just to imagine if we can calculate the total energy of a material, then how, if we have that total energy, how can we get a voltage composition curve? So I really want you to just believe we can calculate total energy, and then how do we go from that to a voltage curve? So this was very interesting to me, 23 or 25 years ago. And, we were trying to understand the voltage composition curve of lithium alloying with tin. So the idea is you start with pure tin over here at the left side. Can you see my mouse?
Yes.
Yep.
And then as you add lithium at room temperature, you move horizontally across this phase diagram, adding lithium as you go, right? So what should the voltage composition curve look like? Well, you can measure it, but can you also calculate it? So John Say was really the theorist that was involved in this particular project. Ian Courtney was a graduate student in my group that went to the National Research Council of Canada to work with John Say for a month to do this calculation. And what you really have to do is you calculate the total energy for tin, lithium 2, tin 5, lithium tin, because this whole voltage curve is just a series of two-phase mixtures. You start with tin, you immediately start to form lithium 2, tin 5. And as you move horizontally from tin to lithium 2, tin 5, the amount of tin in the electrode decreases and the amount of lithium 2, tin 5 increases. And then you move to the next two-phase region, the amount of lithium 2, tin 5 decreases and the amount of lithium tin increases, and so on, okay? So the goal then was to first calculate the total energy of all these lithium tin phases and then see what we could do. Oh, there's the arrow that shows what happens when you add lithium to tin. You move horizontally to the right. So we wrote a paper on the resulting work, and the way this works out is you assume that the structures and the composition of the phases are known. And it turns out for all these lithium tin alloys, all the crystal structures are known. So that means you can take those crystal structures and plug them into a program like VASP and calculate the total energy of those phases. Okay, so you have, how do you get the voltage curve? Okay, so you say, look, I know the reaction that's taking place in the battery. I have a host, all right? It starts as tin, and I can add lithium to that host, a certain amount of delta X lithium. I add to a host that may already have some lithium. If it's already lithium 2, tin 5, it already has some lithium in there. So I add some more lithium, and I get a host that has more lithium in it. So that's the reaction that's going on in the battery when I add delta X lithium to lithium X host. And then if you want to know the change in free energy of this reaction, you would take the free energy of the products minus the free energy of the reactions. But here we work at 0 temperature, so the free energy is the same as the internal energy, which is the same as the total energy. So the change in the internal energy per, let's say, tin atom or per formula unit, depends on how you want to do this, but we're going to say it's per tin atom for the time being, is the total energy of the products per tin atom, where host would be a tin atom, minus the total energy of LIX host per tin atom, minus the total energy of lithium metal multiplied by however many lithiums you transferred from the metal into the host. So all you have to do is calculate the total energies of these different materials and also lithium metal, and know how much lithium is transferred when you move from one alloy phase to the next. And like I say, if you work at T equals 0, delta G is the same as delta U. And the voltages minus 1 over NE times delta G over delta X. So big N times delta X is the same as little n that I showed you on my document camera. And then all you have to do is take this expression for delta U over N and put it in to this expression for V, and you get a simple equation. So if you can calculate these total energies, you can calculate a voltage curve. And that's really what this paper showed. So, like I say, all these crystal structures for all these alloys are known. The lattice constants are known. All the atom positions are known. Everything is known. So you can do these total energy calculations, okay? And you get the total energy per tin atom, per lithium X tin. There's the numbers that you need to do the voltage curve calculation. And you do it. All right, so let's look at the result. So we have the discharge is this continuous curve that's going down like this, where my mouse is traveling. And then the charge is coming back on this continuous curve that my mouse is following. There's a series of steps in the various, a series of plateaus in the two phase regions. And then this dark curve is showing the calculation. So when you go from tin to lithium 2, tin 5, you have a plateau. It's close, within 1/10 of a volt of the measurement on discharge. And the average of charge and discharge, it would be within about 50 millivolts. And then you have another plateau from lithium 2, tin 5 to lithium tin. Again, it's within 50 millivolts of the average between charge and discharge. And then you have another plateau, which again is close to the average between charge and discharge. And then things go awry because the room temperature lithium tin voltage curve does not follow the high temperature phase diagram. So you don't move through a discrete set of phases in experiment anymore. You just go into some sort of crappy mix of almost amorphous stuff. But anyway, the agreement is pretty good where you actually are moving through the observed phases. So we were really quite thrilled by this because it was pretty impressive at the time. So any questions about this? I just want you to get a flavor for how this goes.
I was just wondering what's going on in that kind of region near the Li7SN3. Yeah.
Right.
Yeah,
right here. Yeah. So there's a lot of, in the phase diagram, there's a lot of closely spaced phases here. You can see them all here, right? And what it means is, you know, when you're calculating the total energy of these things, you're relying on the crystal structures and the quality of the total energy calculation to give something sensible. So what happens is you can see the voltage actually goes up in some of these regions because I don't think either the structures are completely right or the total energy calculation is slightly flawed. So this, of course, is unphysical, but that's what the calculations give. That's a good question. Any other questions? You know, so in my opinion, what you just saw, I'm going back to the document camera, which I think you should be able to see now, right?
Yep.
What you just saw is no more complicated than this, where instead of looking up in a book of tables free energies of formation, you're spending the time to calculate the total energy of things when you can't look up these free energies of formation. You know, it's really that simple. Okay, so I'm going to go back to the PowerPoint now. I think you should see the PowerPoint again.
Yep.
We do.
Okay. So, okay, so that's for a simple system where the battery electrode goes through a cascade of single phase regions. You know, you have lithium, you have tin, lithium 2, tin 5, lithium tin. You don't have a continuous composition variation. So what do you do for an intercalation system where you need to calculate many compositions? So talk about lithium cobalt oxide. You know, you want to calculate lithium 1 cobalt oxide, lithium 0.999 cobalt oxide, lithium 0.998 cobalt oxide, lithium 0.997 cobalt oxide, and you get a lot of different, you know, the voltage for each of those things. So you can make a very detailed voltage composition curve. So how do you do it? And, you know, you don't even know where the lithium atoms are. Are they randomly oriented, arranged within the sites? Are they ordered? Where are they? Okay, so what do you do when you have a more complicated system to work on? So what you do is you do total energy calculations for a few structures. So what I mean is you would say, all right, let's take lithium cobalt oxide as an example. We would do a total energy calculation for, say, lithium 1/4 cobalt dioxide with lithium atoms arranged in some particular way. And then we would do a total energy calculation again for lithium 1/4 cobalt dioxide with lithium atoms arranged in a different way. And then we would do a total energy calculation again for lithium 1/4 cobalt dioxide with lithium atoms arranged in a third different way. Okay. And then you would do that for many different lithium compositions across the voltage curve. You might do 10 or 20 compositions with lithium atoms arranged in 3 or 4 different ways. So a whole bunch of total energy calculations, all right? So then you'll have total energies for 10 compositions with 4 different arrangements of lithium at each composition. So for example, here you would, if this is lithium nickel oxide, you would arrange the lithiums in a particular way. So this is for 1/9 lithium. And here's another arrangement of lithium, also at 1/9 lithium. You would do the total energy calculations for these 2 arrangements and others as well, right? And then what you do is you say, these total energies that you've calculated are equal to the sum of a constant plus the sum over the whether the sites are occupied or not. So this sigma I means 1 if there's a lithium on the site and 0 if it's not. There should be a binding energy here. Maybe this U0 should be inside this summation here. But this is like in our earlier treatment, the fact that when you fill a site, there's a binding energy there. So we've got these 40 total energies that we're trying to match based on a binding energy, and then we have 2 body interactions between lithium atoms on sites I and J. They might be near neighbor interactions where I and J are next, or next near neighbor, or whatever they are. And then you might have triplet interactions between sites I, J, and K, etc. And what you're really trying to do is you say, I know where the lithium atoms were in the calculations that I did. I've got 40 results that I have to match. And I'm going to find appropriate values for these different U's so that I can match up these calculations. You know, so we, in our mean field theory, we had U1 for near neighbors, we had U2 for next near neighbors. And here, when you're doing these calculations, you end up with a bunch of U's, maybe 10 or maybe 20, that allows you to fit the 40 total energy calculations with a set of U's. And they work well for all the lithium configurations in those 40 calculations that you did. So here's an example. When Gerd Cedar and his guys worked on lithium cobalt oxide with the spinel structure, here's some things that we can recognize. Here's a nearest neighbor octahedral pair interaction. This is between two lithium atoms put on near neighbor octahedral sites. We would have called that U1, okay? And here's near neighbor's tetrahedral octahedral pair. So you can see this is a much bigger interaction energy. So this would very much not like to happen. The tetrahedral and the octahedral sites are much closer than the near neighbor octahedral pair. And then he has a near neighbor tetrahedral pair. It's a pretty small interaction energy. And one of the reasons is the tetrahedral sites aren't in the middle of the lithium layer. Okay, but in any event, he's got all these different things. A triplet of octahedral sites that are filled, all these different interactions. Which ones did they pick? Well, they're telling you. Why did they pick these? They're not telling you. They could have picked other interactions to try to fit their, in their case, 17 total calculated total energies. So they used 10 of these U's to fit 17 calculated total energies. How accurate is this? Well, these numbers are probably pretty accurate, but what happens if you change the interactions that you consider? So there's a lot of art involved in all of this and so on. Once you have this expression, then you have to do the full statistical mechanics calculation, where you do the entropy correctly, not with the mean field approximation, and that's done with the Monte Carlo method. Okay, so the long and short of all of this is you can do a calculation. There's a lot of art involved because you have to calculate the total energies for quite a few structures with lithium atoms arranged in different ways. Okay, and then once you want to get finally the chemical potential and the voltage versus lithium content, you use Monte Carlo methods to do the statistical mechanics properly. So here's the result of a calculation. And what they've done here is they've calculated the voltage curves for spinel lithium cobalt oxide, which is the dashed line, and layered lithium cobalt oxide, which is the full line at roughly room temperature. Okay, so those of you that know what the voltage curve of lithium cobalt oxide looks like, layered lithium cobalt oxide, you'll say, well, it's roughly the right voltage, but really lithium cobalt oxide comes up to about 3.8 volts. It goes pretty flat over to here. There's a little bump around 4.05 volts, about the size of this bump due to lithium ordering. Then as you go more, there is no bump here. And as you go up into this range, there's a double, 2 plateaus and a bump. So this calculated curve doesn't really match experiment so well. And if you know anything about the voltage curve of spinel lithium cobalt oxide, probably you don't, it does have a lower voltage plateau, but it does not show this gigantic step in the middle and this upper plateau. It's sort of, it doesn't look like this. So to get really accurate calculations of voltage curves, I would say is quite difficult. But if your goal is to say, is the voltage close to 4 volts or close to 2 volts? That's okay. You can learn that. And maybe you could say, is the voltage close to 4 volts or close to 3 volts, and be pretty confident of that too. And for some systems, maybe the agreement between the theory and experiment can be better. But don't think that a computer is going to take the job of an experimentalist away in terms of accurate voltage curve determination. It's not going to happen. So, any questions about this part before I go on to a little bit more about what these total energy calculations can be used for and some of their successes?
Hey, Jeff?
Yeah.
I remember you saying that octahedral sites get filled first before the tetrahedral sites. But in that table you showed a few slides back, they were showing that the near neighbor tetrahedral interactions are lower in energy. So how come the tetrahedral sites are not preferentially getting filled first?
It depends on the site energies, right? This is an interaction. It's a pairwise interaction. So I don't know how to read this and say what is the energy filling associated with filling a tetrahedral site. And actually this is for spinel. So in this spinel, maybe the tetrahedral sites are filling first.
I see, okay.
Any more questions about this? All right, so we'll go on. So don't think that this theory is not very useful. It's incredibly useful. So this is a slide that I got from Gerd Cedar at one point, where they show their successes here. So they showed clearly what would happen if you added aluminum to lithium cobalt oxide. The voltage goes up. And this has been experimentally verified as well as by theory. Okay. And they found this particular material, they predicted that it would exist and it would have a high voltage, and that was found. They also predicted the H13 phase, the stage 2 lithium cobalt oxide phase at high voltage. This graph you might recognize looks like a format of a graph from our lab, and it's taken from one of our papers. And they also predicted a way to make high rate lithium nickel manganese oxide 50-50. People like Aaron Liu will tell you, what does high rate this mean? Because everything we make is very low rate because there's a lot of exchange between nickel and lithium. The nickel layer is not pure nickel, and the lithium layer has lots of nickel in it that screws up the diffusion of lithium. So what they did was predicted you could make high rate lithium nickel manganese oxide if you had pure lithium layers. And then they made this material by ion exchanging a sodium nickel manganese oxide material. And for the first few cycles, it did have high rate capability, but then cation exchange occurred in the cell itself, and the rate capability became crappy.
Hi, Jeff.
Yeah.
So for this slide, normally during the Tesla conference call, you when you were talking about the results from the cathode group, you often say like lithium in the nickel layer. Is this similar thing? Like the nickel goes into the lithium goes into the nickel layer and slow down the diffusion of lithium?
Yeah, when the nickel goes into the lithium layer, it slows down diffusion. That's correct.
So
yeah.
that's common for not just these materials, but for other NMC materials, right? Because you normally during the Tesla conference call, you always talk about when they synthesize new cathode materials, you always talk about what is the percentage of the lithium in the nickel layer, nickel in the lithium layer, the opposite.
That's correct. Nickel in the lithium layer. Nickel in the lithium layer is in general bad. It slows down diffusion. In fact, Nanofon is going to have an amazing work of art paper coming out in a couple more weeks that we can share once it's finished being written, which is almost done.
Okay, thank you.
Okay, so let's move along. So this was in a paper from Gerd Cedar, which was very nice, okay? So what they did here in this calculation is they spent the time figuring out how much energy was required to remove an oxygen atom from delithiated materials like nickel oxide, cobalt oxide, and so on. Is the oxygen, this is like an oxygen binding energy chart that you have here. And if you think about what happens when a lithium ion battery is fully charged and it gets super hot, well, the cathode materials tend to evolve oxygen into the heated electrolyte, and then you can get severe thermal runaway. So anything near the top of this chart is expected to be very unsafe in a fully charged lithium ion cell. And here's nickel oxide up here at the tippy top. And we know from our experience that lithium nickel oxide is incredibly difficult to make a safe lithium ion cell. And fully charged lithium cobalt oxide is virtually as bad. And then when you look down this chart, look where LFP, charged LFP, is way down here, right? And the surprising thing about this chart is manganese phosphate was way up here, right? So you would wonder, where is LMFP, which is a combination of iron and manganese? And we learned through experiments that Dongshu did that lithium manganese iron phosphate with 80% manganese and 20% iron was as safe experimentally as iron phosphate. So it makes you wonder about this particular calculation for manganese phosphate, that it would be predicted to be so much worse than iron phosphate. And then finally, if you're worried about lithium manganese oxide spinel, when you remove all the lithium, it should be much safer than the layered systems here. You know, so these type of calculations are sort of a bonus that you can do in this total energy calculation stuff. You can learn a little bit about safety, but again, you have to take the theory results with a grain of salt, because sometimes they've been proven to be not right. This is a very nice paper from the Gerd Cedar group about a new set of materials, carbonophosphates. So in the materials project, the Cedar group identified this material. They said, okay, we should be able to make this thing. It should form. They predicted what its voltage curve should be. They made it. This is what it looks like. Predicted theoretically, they made it, and it has, you know, a charge discharge curve, and 100 milliamp hours per gram cycling, and so forth. So this was an example where they took tons of known crystal structures and then substituted different atoms at different sites. So if you had a structure that was a known iron-containing material, say an iron phosphate or whatever, and then you stick every other positive cation instead of iron, just replace it by everything else. See if it would be stable, calculate its properties, its lattice constants, and so forth. And also, you know, develop structures that, you know, maybe we're not known, but then we're calculated to be stable, and then explore those experimentally. So it's pretty cool. So I don't want to spend a lot of time on this ab initio stuff because I'm not really an expert in it. We were involved at the very beginning with very simple things. So I'll give you something to read and think about on a homework. I will say, though, that one of my students, Vincent Chevrier, did some really nice work on amorphous lithium silicon. So, you know, in this case, you don't even know the structure of the host. You don't even know where to put the atoms to do these total energy calculations because it's amorphous. So how do you do this from first principles? Anyway, so Vincent figured out how to do this with some help from, oh God, what's that guy's name? Normand Mousseau at University of Montreal. And was able to calculate the voltage curve of amorphous lithium going into amorphous silicon. So adding lithium is the red curve. Taking lithium out is this red curve here, discharge and charge, and this black curve, black solid curve, is Vincent's calculation, which matches the midpoint of experiment, you know, really well. So we were very pleased with this. It was a huge amount of work. Like, don't think this is something you can just say, oh, I'm going to do this in my spare time. It took a year or more to do this work. So anyway, you know, this field is fairly well developed, and you can get quite valuable information from it. It's not like putting bread in a toaster. You know, you don't just push a button and the results come out. And those of you who know what Marc Cormier in our group is doing, Marc does this type of work. And, you know, Marc's made some very nice contributions to our work on nickel-rich materials in the last couple of years. All right, anyway, so I'm going to stop here, and I'll just tell you that Wednesday, if you remember, we have the NMR battery webinar. It starts at noon. I'm not sure how long it goes. I want to go to it myself, so that's why I don't want to have class on Wednesday. So we're going to skip class on Wednesday. I hope that you'll all go to this use NMR methods for studying lithium-ion batteries webinar, 12 o'clock. I sent you the link for Wednesday. And then we'll come back on Friday. And on Friday, I'll start a topic called real lithium-ion batteries. So we're not going to be talking about basics anymore, about structure and voltage curves and all that kind of thing. And many of you are going to say, finally, he's doing something useful, I suspect. But all these basic things are very useful, because if you don't have a solid foundation, you can't build a house. Okay, any questions about this stuff from today? All right, like I say, I'll give you a homework that has some, you know, you can take a look at what can be done with these theoretical methods. I'll let you explore the so-called materials database. and see what you can learn from that. And I hope that you'll attend the webinar on Wednesday, and I also hope that it's useful and not a waste of all of our times. And I'll see you back again on Friday. And I'll send you the notes for Friday as well.